So we take it for granted that plants will burst bud in the spring. But have you ever stopped to think about how they know when to burst bud? They don't have an alarm clock that says, oh, it's time to go now, or they can't look at a calendar. But really, it's quite an interesting process, because if they burst bud too early, then they get hit by frost and the new foliage is killed. If they burst bud too late, they don't have enough time to get their new growth out before drought stress hits them. So really, timing is everything when it comes to bud burst. So how did they do this? There's a couple graphs you have to suffer through. I couldn't think of any way to explain this without having some graphs. But basically, plants have a memory of what happened in the winter. And in scientific terms, we say that they have chilling and forcing requirements, meaning they have to have experienced some cold temperatures and they have to experience some warm temperatures before they'll burst bud. So this blue graph here is the chilling requirement. And the interesting thing to see is that it's kind of an unusual shaped curve. And temperatures down below freezing have either no or very limited effectiveness. And temperatures, these warmer temperatures, are not very effective. And then there's this kind of sweet spot of temperatures that are really effective. And then the forcing is kind of a normal shaped curve, as you would expect. And I'm not really going to talk about forcing. So this is the most complicated graph in my presentation, but it's one that I think is important. And that's that there are many combinations that can result in spring bud burst. The plant is accumulating chilling and warming and chilling and warming, and it can have until it gets up to this line here, which I call the possibility line. And when it gets to the possibility line, it means now bud burst is possible. But there are lots of ways to get to the possibility line. So you could have a lot of warm temperatures, you could have all kinds of combinations in between. But whenever the combinations of chilling and forcing are in this gray area, bud burst or terminal bud burst is not possible. One thing to notice here is this line goes up straight in this particular case. And that's true for all species that have an absolute, or what's called an obligate, chilling requirement. And that means that it doesn't matter how much warm temperatures they get. If they don't get a certain amount of cold temperatures, they absolutely will not burst bud. So what we've been doing in the last few years is developing possibility lines for different species, and also in some cases for different populations of species. The one that we have the most information on is Douglas fir, which is the kind of dark blue line. Most of these go up to that kind of straight line, meaning that they do have an obligate chilling requirement. The one here down at the bottom is madrone. And this is western red cedar. And it's kind of interesting over here, once you understand how these curves work, is that these species over here, the madrone, this is western larch, and the red cedar, if they have a lot of chilling, they require very little forcing to get them to their possibility line. So if you're going down along here, if you've got a lot of chilling, just hardly takes any forcing at all to hit your possibility line. And many of you have known that western larch is often the first one that'll burst bud in some of the higher elevation communities, so that makes a lot of sense. But in addition to looking at different species, we can also look at different populations within a species. So in this case, we have a sheaf of possibility lines for Douglas fir. And the one on top, the blue line, is for the Washington coast, and the one on the bottom is for the California Sierra. And with a lot of chilling, there's not a lot of difference between those lines, but if you're low on chilling, there can be a substantial difference. The little graph over in the corner here, these are two lines for some populations of madrone. So this lowest line here is some madrone from a very warm California and then this is one from some more northern. So one of the neat things about this kind of mechanistic model is that we can use it to look both backwards and forwards. So in this case, we took climate data or weather data from Olympia and Salem for individual years, so back from the 1950s into the early 2000s. And then we were able to use the model to predict the date of budburst for each year. There are two points that I'd like you to see in this graph. One is that there's a tremendous variation from year to year. So here we have day of the year for budburst up around day 150, and then at the same location you could have down here at 110, so a difference of like 40 days or more. And then the second thing is, even though there is a tremendous amount of variation, there is a downward trend to those lines. So on average, budburst is happening 1 to 2 weeks earlier, these locations based on our models. And the models actually run on hourly temperature, but the basic relationship holds that mean winter temperature is very closely tied to prediction of spring budburst, the date of spring budburst. And so many people have heard of this before, this phenomenon that the predicted date of budburst is earlier after warm winters. And for example, there have been articles in the newspaper about lilac trees and national networks blooming earlier and other types of things. And the morning speaker talked about primrose blooming earlier in China. But one of the things that our data shows, both our research data and our models predict, is that the trend will reverse. So as the winters continue to get warmer, budburst will then start happening later. And the reason for this is back to this blue curve here. As the winters get warmer, those temperatures have less and less effectiveness for chilling. So just to give you an example, this is based on recent, in the past 10 to 15 years, we took years that had substantial amount of climate data in Northern California, Washington, and Oregon, within the range of Douglas fir. And we predicted the date of budburst for all those stations. And then we interpolated between those stations based on latitude, longitude, and elevation. And so this is a representation of budburst with red being early and blue being later. So with the model, we can predict what is going to happen in the future, in this case from the climate WNA model up from the University of British Columbia. It's kind of hard to see those different graphs, so we did this math magic where we take the date of budburst in the future minus the date of budburst now, and we look at the difference. So this color ramp now is showing you the change in the date of budburst between the historic values and the 2080 values. And you can see the dark green values are showing 60 or more days advance in the date of budburst, and the yellow is down in the 10, 20, 30 days. But you can see that the model does predict some areas that have negative values, but because of the color ramp, you can't see them too easily. So I'm showing them on the other side of the screen. The red points are the ones that actually are showing later budburst in 2080 as opposed to earlier budburst. So what would happen is that budburst would be happening earlier, and then it would kind of pause, and then it would start going back, and then as the climate continues to warm, we actually would end up with later dates of budburst. So you can see on the right how rapidly budburst progresses during the season in the future compared to the much slower progression that is currently happening. And we can do similar things for other species. In this case, sometimes people wonder why the maps are cut in different ways, and those are cutouts based on the current range of the species. So sometimes people say, okay, well, modeling is all that well and good, but does that really happen? What's really going to happen if things get warmer? And so the models were actually based on data from a lot of different sources, including a series of greenhouse and growth chamber experiments. But I'd like to show you what some of the trees actually look like. So Douglas fir, if it has very low chilling, as I mentioned, it has this obligate chilling requirement. And under extreme conditions of low chilling, the terminal bud does not actually burst. But what happens is that these side branches take off. And so even though the plant is actually bursting bud, the terminal bud is not, which is going to result in very ugly-looking trees in the future and lower growth rates. So just looking at that for a couple other species, this is grand fir, low chilling environments on the left, greater chilling on the right. And you can see the greater growth rates, and also the ones with low chilling are often having multiple tops. Western white pine, you see not only the shorter shoot here, but here, even when the shoots are longer, they have very short needles. And the needles are only on a portion of the shoot. This is lodgepole pine. You see the same kind of thing. You get these long shoots with long needles on them, and here you're getting shoots. The shoot elongated, but it never actually burst bud. There are no needles on that shoot for the year. Here we got some new needles and some multiple tops. Madrone. Madrone is a completely different species. It didn't really care what it was like in the winter, or cared to a very small degree. These trees were quite small at the beginning, way down here, and they were extremely happy to be in the greenhouse. They did not have a chilling requirement, or the requirement is exceedingly low. Western red cedar is another one that also has a relatively low chilling requirement. The plants grow better if they're chilled, but when they do respond, when they do grow, they look very normal. So they don't get these oddities that some of the pines and the true firs do. So I hope I've persuaded you. My one-sentence conclusion: winter temperatures matter. Warmer winters affect the tree futures. They affect the timing of bud burst. They affect the future growth. They affect the form of the tree. So winter temperatures do matter. Place matters. It matters what your current environment is. It matters what your temperatures are currently. Some sites are, some locations have more sensitive. They're already close to the limit for winter chilling. In terms of management, genetics can help. That is, there's some species that are going to be less sensitive to warmer winters, and also seed sources can differ within some species. So I think it's, there is some hope out there that there are some ways that we can respond to warmer winters. Thank you.